Welcome to the afternoon session. Our first speaker is Thomas Rothvoß, and he'll talk about extended formulations.
Okay, welcome to the tutorial on extended formulations. We'll do this together with Hamza and Prasad. And we have 4 lectures divided by 3. So, the plan is we'll give everybody 1.x lectures. Doesn't have to be the same x. Doesn't have to be positive, probably. We'll see how this turns out. So the plan is that I'll give some introduction into extended formulations for linear programs. Then Hamza is taking over, and he's going to talk about how you can have extended formulations for semi-definite programs and what happens in that case. And the plan is that Prasad is going to talk about 2 lower bounds that he and co-authors proved for some LP setting and also some SCP setting, which is a pretty recent bound. Okay, so let's see. So what is an extended formulation? In combinatorial optimization, what we love to do is we love to look at polytopes, and usually they're given in some inequality description. And there's a different way how you can represent polytopes. You can imagine that you're adding some extra variables, and now you're looking at inequalities in a higher dimensional space that also contain these extra variables. And now you may want to write your polytope as the set of all x, so that there is a way to set your extra variable so that other system of linear inequalities is satisfied. And if you think about this geometrically, then this means that you have your actual polytope, but you write it as a linear projection of some higher dimensional polytope. Okay, so why should you go to some higher dimensional space? The idea is that there are many examples where the original polytope needs exponentially many constraints, but it's possible to go to some higher dimensional space and only use fewer inequalities. Let's say polynomial many inequalities. And the study of extension complexity is, by how much can you reduce the number of inequalities by going to some higher dimensional space? So more formally, the extension complexity of a polytope, it's the smallest number of inequalities that you need so that you can write your polytope as a linear projection of some higher dimensional polytope with that many inequalities. And you're kind of ignoring the dimension here. You only count the number of inequalities. Okay? Good. So I have to pay a copyright fee for every minute that I'm showing this picture to Sam Fiorini. So let's move on. And it's going to be an expensive talk. Okay. So what's the motivation? Okay. So imagine you have the spanning tree polytope. So the spanning tree polytope, it's the convex hull of the characteristic vectors of all the spanning trees in let's say, a complete graph. Maybe this one, and that means like every of those corners would correspond to one spanning tree. And imagine you want to use linear programming to optimize over that polytope to find the cheapest spanning tree. Then the problem is that this polytope has exponentially many constraints, and it also has exponentially many vertices. But there is a way how you can write this in a higher dimensional space by adding some, let's say, flow variables, and only have n cubed many inequalities. And then instead of optimizing a linear function over the actual polytope, you can just optimize the same linear function, added with some zeros, over the higher dimensional polytope, and you get your answer. So you can get your answer by just solving a linear program that has polynomial size. And that's a nice thing. Okay. On the other hand, later we will see some lower bounds on the extension complexity. And the lower bound on the extension complexity kind of implies that there's a certain class of algorithms that you cannot use to solve your problem. So in particular, you cannot solve your problem by just solving one polynomial size linear program. Okay, so that's a little bit the motivation. Any questions so far? So I thought I'll start with one concrete example. Otherwise, things are maybe a little bit too abstract. And my example is not going to be spanning tree, but my example is going to be the knapsack polytope. OK. So knapsack, probably all of you have seen that problem. Here we go. You have n objects, and every of those objects has some weight. Imagine that being some positive integer, and it has some profit, pi. And you have a knapsack, and the knapsack has some capacity, let's say capital B. And now the goal is you want to find that subset of your items so that the sum of the weights does not exceed the capacity of your knapsack, but you want to maximize the sum of the profits. Just good old knapsack. OK, so it's a very well understood problem. It's NP-hard, weakly NP-hard to be precise. And there are pseudo-polynomial time algorithms. So if the weights are bounded by the polynomial in n, then you have a polynomial time algorithm. In particular, there's also an f-betas for the problem. What's a little less known is that there is also kind of a nice extended formulation for it. And let me explain this. So if you look at this object here, this is the convex hull of all the characteristic vectors of solutions so that, well, these are feasible knapsack solutions. And if you look at the convex hull, then the extension complexity, it's less than you might think. It's bounded by n times capital B, and B is the size of your knapsack, assuming that the weights are integers. OK? So this kind of looks like the running time of some of that pseudo-polynomial time algorithm, if you think about it. And I want to explain this. And in some sense, well, it's an NP-hard problem, so you don't expect that there is something polynomial in n. That won't happen. But there's a pretty neat extended formulation. Any question? OK. And the trick is that you just use that dynamic program that's behind those pseudo-polynomial time algorithms. And here we go. OK, so you'll probably have seen this type of dynamic program before. This is the dynamic program that just is the algorithm to solve knapsack in n times capital B. And you just need some table entries in your dynamic program. Let's call this, it's a table entry depending on some index I and some parameter W. And this is just supposed to be like the maximum profit that you can get by taking a subset of the first I items so that their weight adds up to precisely W. And this is just the formal definition of that. OK? And there's a very simple way how you can just get every entry in this. Then every of those table entries, you just take the better option of, well, if I take the ith item, then I get the profit from the ith item, but like the weight that I have left decreases by the weight of the ith item. And if I don't take it, then I just copy paste the entry from the left-hand side column. OK. Good, so this is a dynamic program, and this directly can be translated into an extended formulation. As follows. OK, so we have table entries for every index I and every W that's between 0 and the capacity of the knapsack. And let's arrange them in like a matrix form. So this is index 0, index 1, index 2, and so on. And this is weight 0, weight 1, weight 2, and so on. And let's create a network as follows. We're adding two types of edges. We consider like every of those nodes as a state. And we're adding a directed edge between a state and the neighboring one. And we imagine that we give a cost of 0 to this edge. And these edges correspond to these decisions that I don't want to take the ith item. Okay, so we're also adding edges between state I minus 1, comma w minus wi to the state iw, and these are the edges that correspond to the decision that I want to take the ith item. So I want to go from this state to this state, and I'm making some profit if I make this decision, and the profit is precisely the profit of the ith item. Okay, and if you now think about this, then then I can also add a source, and I just connect the source to the state, to my start state, which is just I equals 0 and w equals 0, and I add a sink, and the sink has cost 0 edges, profit 0 edges from all the states for I equals n, and w at most the capacity going in. And now there's an easy bijection between every subset of your items, so that the sum of the weights is at most the capacity of the knapsack and the path in the network. Okay? So this is actually just what your dynamic program is doing. Your dynamic program just looks at the maximum cost path from S to T in this network. Okay, now we have everything nicely in place. Now we just need a linear program that finds us the maximum cost path in this network. Okay, and well, that is a well-known thing. Essentially, the idea is you want to send a flow of capacity 1 from S to T, and you want that the cost of that flow is maximized. Okay. So, okay. So this is our network, and this is just the linear program. You'll need some flow variables that are called y, and the flow, it should be a flow that sends a flow of 1 from the source to the sink, and at every other node, you want that what's coming into the node minus what's coming out of the flow is 0. Okay, so this models your flow. Yes, Prasad.
What do you mean by item I edges?
Okay, so item I edges, for example, item 2 edges are these 3 green edges. They correspond to the decision that you want to take the I equals 2 item. Good. Okay, so we have this flow of value 1 going through our network from the source to the sink. Okay, and now there should be the projection back on the knapsack variables. The way how we can do this is like the projection. You could just do the following. You have these variables these flow variables that correspond to should I take the ith item or not, and you just sum them up, and that gives the decision whether I should take the ith item or not. Okay. So there are some things that you would actually need to prove. You would need to prove that all the extreme points of this polytope, they are integral. There are basically 2 ways how you can do that. You can stare long enough at the constraint matrix. You see that you have 1 and minus 1 and 0 entries, and the matrix is actually totally unimodular. A more direct way would be that you say, well, if I don't have an extreme point, then if you look at the residual graph of the flows, you would need to have a cycle. Then you can change the flow, and then, I mean, you're showing that you don't have an extreme point. Okay. Good. So if you think about this geometrically, these are your xr variables. You get something in a higher dimensional space where you have those flow variables, and if you project things down on the knapsack variables, then you have a beautiful 0-1 polytope. Okay? Too easy? Okay. Okay, so the size of this linear program, it's basically the size of the network, so it's O of n times b. That's the number of constraints you're having. Also, it's the number of variables that you're having. Okay. By the way, there's a nice open problem here, which is the following. Okay, so I mentioned that there is an f-pitas for Knapsack. So is there also some type of f-pitas in terms of extended formulations? So what would that mean? Well, let's look at the knapsack polytope. So this is the convex hull of all the solutions to your knapsack problem. But maybe now these are nestedly large numbers. You don't want to write down this network, which would be giant, which would have a giant size. You want to approximate this polytope. So let's say what you want to have is you want some other polytope that's inside of that nasty knapsack polytope, and you want that if it's scaled by 1 plus epsilon, then it contains your knapsack polytope. Why would that be nice? It would be nice because if now someone comes down the road and he gives you some costs, some profits for the items, you could just optimize that linear function over k, over your small linear program k, and you would get a solution. That's a 1 plus epsilon approximation to the actual knapsack problem. And we know that there is actually an algorithm for that. So the question is, could you get an f-pitas for knapsack by just solving one linear program? Okay. So what I would like from this linear program is that the size should be polynomial in n and in 1 over epsilon. So that would be yes.
Did Beanstalk have something like results along these lines?
Okay, what Beanstalk shows is that you can get a kind of a pitas approximation using a linear program. I'm sure we'll see the Shirladi-Adams hierarchy. You could basically, later in this workshop, and you could basically use the Shirladi-Adams to get this type of result. But this does not give you an f-pitas type approximation. And if your idea is that, oh, let's just take the weights and let's just round the weights a little bit, and then have that compact LP that I just showed, that would not give this result, because you might get slightly infeasible. You might have some solution that's just barely on the border, and if you round some weight, then suddenly this may become infeasible. Okay. Okay, so this is a nice open problem. If you have a
lower bounds. So what do we know in terms of lower bounds for this?
I don't have any non-trivial lower bound except like dimension or so. Okay, so you have 3.5 months to solve it if you like, and we'll see at the end what comes out. Okay, so this is my introductory example, and now I want to talk a little bit about some structural background behind extension complexity. Okay, so I cannot talk about the extension complexity without talking about slack matrices, and here we go. So let's say you have some polytope P, and imagine you have it given in two different representations. So on the one hand, I tell you all the inequalities describing that polytope, and on the other hand, I give you the vertices describing the polytope. Okay. Yes.
Before we go to slack matrix, so that previous example was essentially had an algorithm implied the existence of an extended formulation. And
no, the extended formulation implies the existence of an algorithm.
Oh.
He's saying the dynamic program.
The dynamic program somehow implied.
Oh, okay. The existence of the dynamic programming algorithm implies the extension complexity.
But it's very specific to that. Like I was getting.
Yeah, in some sense, if you show a lower bound on extension complexity, it shows that this simple class of dynamic programs can't exist for that problem.
I see.
It's like where you have like a polynomial number of states, and you have some decisions, and you always take the maximum over something that like linearly depends on your cost function, something like this.
I see. So the functions themselves kind of look polyhedral.
Yeah.
Yeah.
Does running the simplex method over the LP you get model what happens in the dynamic program? Like if you have this extension, this lift you get from the polytope, you could run the simplex. You could solve the LP does it do the same thing as a dynamic program?
Okay. For this one, well, depends. Probably depends what rule you have in the simplex method.
I think you do network simplex and
Yeah, someone volunteered for a different tutorial on the network simplex. So. Thank you, Michelle. Okay, other questions? Okay, so Slack matrix, yeah. Okay, so a Slack matrix, it's a giant matrix where you have a row for every inequality describing your polytope, and you have a column for every vertex describing your polytope. And the entry that you have, it gives the slack that this vertex has with respect to that facet. So it's, well, depending on the scaling, but it's proportional to the distance of the vertex to that hyperplane. Okay, so this is a giant matrix with only non-negative entries. That's important. Okay. A second definition that's going to be important, it's the non-negative rank. So first of all, the usual rank of a matrix, it just means the following. You want to write a matrix as the product of two matrices, and you try to minimize the number of columns that the first matrix has and the number of rows that the second matrix has. But the non-negative rank, it's a restriction where you're forced to use only non-negative matrices. So then the non-negative rank, it's going to be something that's always at least as big as the rank, but it may actually be a lot larger. Okay. Okay, so why am I mentioning like the Slack matrix and the non-negative rank? There's a beautiful theorem of Yannakakis from the late 80s showing that actually if you look at the non-negative rank of the Slack matrix of a polytope, that's precisely the same as the extension complexity of the polytope. So if you do figure out the non-negative rank of the Slack matrix, you have precisely the size of the smallest LP modeling your problem. Okay, the first time you see this is like, why should this be true? It does make a little bit more sense if you look at the proof. My students never believe that when I say it, but okay. So, okay, let's see the proof, and the proof obviously has two directions. And this is the supposed to be easy direction. Okay, let's say this is your Slack matrix, and you manage to factor it as U times V. These are non-negative matrices. So how do you get an extended formulation out of that? Well, let's say this is your original polytope. It's AX at most B. Now you take this and you slightly modify it. You write it as all x so that there is a non-negative vector y, so that ax plus the left vector times that non-negative vector equals b. So the inequality turns to an equality. So why would that make sense? Well, first of all, if you have a point that should be in the polytope, that should be in P, let's say a vertex, then you can actually you can make a choice for y so that this is true, and you just, if this was the jth vertex, then you just pick the jth column of the right factor, and you plug it in here, and the inner product of this row and that column is precisely the slack that you need to make this inequality. Okay. On the other hand, if you have a point that's not supposed to be in the polytope, so you have a point x so that for some row I, aix is bigger than bi, then whatever non-negative stuff you're adding, still this is bigger than that. So there's no way of getting inequality. Okay. So that actually means that if you have that factorization that gives you a non-negative, that gives you a representation where, well, I'm not actually saying much about the number of equalities, but the number of variables doesn't go up too much, and that also bounds the, well, you can reduce things, and then you also get an extended formulation that has that bound on the number of constraints. Okay. That was a little cheating, but okay. So there's a second direction.
Real quick, just go back. I just wanted to first. Okay. So that last thing is because the U is a non-negative matrix factorization, and the Y we're assuming has to be non-negative. That's why that last under bracket.
Yeah. Yeah. Okay. Okay. Maybe slightly more interesting is why the other direction works. Okay, suppose this is your polytope and you have a nice extended formulation that has only few inequalities, R inequalities. So why does it mean that you can get a factorization of the slack matrix that has only R columns in one matrix and R rows in the other one? Okay, so let's think about what do we actually need. We need non-negative vectors ui and vj that both have dimension r. They're non-negative, both have dimension r, and we have a vector ui for every constraint I, and we have that vector vj for every vertex xj of the polytope. So, and from somewhere we need to get those non-negative vectors. And if you look at the inner product, it better be the slack that this guy has with respect to that inequality. And this is where we get things from. So that vector for ui, we get it as follows. We look up in that higher dimensional space, in that higher dimensional polytope, and by LP duality, you can figure out that there has to be some negative combination of the constraints that gives actually this vector here. Otherwise, this would not be the projection of this thing. Okay, and you take those you take this conic combination, this non-negative combination, and you use that to fill your vector for this constraint. Okay, similar game here for the vertex. You look up into that higher dimensional polytope. You're gonna hit at least one point here, and you now look at this feasible point. What are the slacks that this point has with respect to those R many constraints? So you get R non-negative numbers, and you use these R non-negative numbers to fill that vector vj. Okay. And now you just multiply things out, and then kind of more or less magically you get the slack. On the other hand, now if you think about the picture, then, well, you take a conic combination, you take a non-negative combination of some slack values, that you're getting like the slacks of this thing with respect to this one kind of makes sense if you look at the picture. Okay. Questions? Okay. Good. So this is a Yannakakis theorem. Okay. So if you talk about the extension complexity, you may want to show an upper bound that usually you show by giving some construction of a linear program. You may also want to show some lower bounds, showing that actually for some polytopes you need a certain number of constraints, even if you go to a higher dimensional space. And I want to talk about kind of the simplest method how you could possibly get a lower bound. Okay, and that's the so-called rectangle covering number. Okay, so here's the principle. Imagine this is some non-negative matrix S, and if I didn't mess up, then this should be a non-negative factorization. U times V should give S. Now I want to convince you that the non-negative rank of this matrix is at least something. You can actually do the following. You can forget the numbers and just remember whether numbers are 0 or whether they're positive. We don't have negative numbers. So. Okay. Now, if you look at the first row of U and you look at the first column of U and the first row of V, and you look at the positive entries, then they actually induce what's called a combinatorial rectangle. And in that combinatorial rectangle, the matrix is only going to have positive entries. With a positive entry times a positive entry, it's going to be positive no matter how many non-zero entries, how many non-negative entries you're adding. Okay, so if you complete the reasoning, then you get that actually, if you only had R many columns, then you can actually cover all the positive entries of your select matrix using only R combinatorial rectangles. In particular, those combinatorial rectangles are not going to cover any of the 0 entries. Okay, so if you manage to show that your select matrix has a rectangle covering number that's at least, say, 2 to the n or 2 to the constant times n, then you have your lower bound. This is kind of nice in the sense that it's something more combinatorial. You don't have to mess around with the numbers. You just have to show a lower bound on the pattern of this support pattern. Okay. Good. So rectangle covering and these notions like combinatorial rectangles, there's an area in theoretical computer science where you may have heard these words before. And these terms kind of come from what's called communication complexity. I think there was a workshop, like 2 workshops ago or so. Okay, so there's indeed, there are some beautiful connections to communication complexity. If this is just back in your dark undergraduate times, let me try to remind you what that is. Okay, so the general setting in communication complexity, it's the following. There's some function f that depends on 2 inputs. Let's say some input coming from capital X and some input coming from capital Y, and let's say it just gives you some number. And you imagine that you have 2 players, Alice and Bob, A and B, and Alice gets 1/2 of the input. Let's say Alice gets the input from capital X, and Bob, he gets the input from capital Y. And now they want to figure out what is actually the value of the function. And what they can do is they can send bits to each other. And after some number of bits, they should both know the value of the function. Okay. There are some differences in whether there's randomization, whether things should be deterministic, non-deterministic. Okay. So this is a kind of the general setup in communication complexity. Good. So where's the connection now? So imagine like things are deterministic for a moment. And let's look at what's called the decision tree. So the decision tree is the following. This is at the beginning of the protocol, and then let's say Alice either sends a 0 or she sends a 1, maybe then it's Bob's turn, then Bob either sends a 0 or a 1, and so on, and the number of bits they exchange is the length of the protocol, corresponding to the depth of the tree. And okay, so at the end of the protocol, they are sure that they both know the value of the function. And okay, I should mention that usually the way this is interpreted is that it's like the function corresponds to a matrix, and Alice gets an index, gets a row index, and Bob gets a column index, and they have to figure out like what's the entry in the matrix. Now, obviously, that's the same as figuring out a function. Okay, so now what happens if the protocol kind of goes down this way, so they exchange 0, 0, and then they're sure that they know what's in the matrix. Maybe they're sure that the matrix entry is 2. Then actually Alice doesn't actually know precisely the input of Bob. She just knows enough to be sure that there's a 2. Bob doesn't actually know what input Alice has. He just is sure enough that the entry should be 2. The matrix entry should be 2. So actually what happens is that the set of inputs for Alice and Bob that lead to go down this path in the protocol tree, it must be a combinatorial rectangle. The value of the matrix must be the same. Okay? Because otherwise there would be a mistake in the protocol. They couldn't be sure. Okay. So if you think about this, then if you have a protocol where Alice and Bob exchange C many bits, then you have 2 to the C many leaves, and you have a partition of your matrix in 2 to the C many rank 1 matrices. Okay? And a partition of your matrix in 2 to the C many rank 1 matrices, and that just means you can write your matrix as 2 to the K, if that was K, many, actually these are non-negative rank 1 matrices. So this is just a factorization, this is just a non-negative factorization, and this is the size of your non-negative factorization. Okay? It's just the depth of 2 to the depth of the tree. It's the number of leaves of the tree. Okay? Yes, Pablo.
So does this capture, for instance, if they decide to send either 1 or 2 bits, depending on the result of previous exchanges? Or somehow the structure of the tree?
Okay, so
somehow they always alternate sending bits, or?
Okay, so first of all, you're only losing a factor of at most 2 in the depth if you require Alice and Bob to alternate, but they don't have to alternate. So it could be that if Alice sends a 0, then later she will send another bit, and if she sends 1, then it's Bob's turn. So that would be a protocol as well. Okay, so, I think I did skip this notation. Let's say the communication complexity of a function or of a matrix, it would be just, it's the number of bits you need to exchange in the best protocol, in the shortest protocol. Okay? Good. Okay, so, okay. So I hope I could convince you that the following is true. So the extension complexity of a polytope, we just saw that it's actually bounded by 2 to the communication complexity of the slack matrix. Okay. It doesn't look very good if you have an upper bound which is 2 to the something. But there's a beautiful application, for example, to perfect graphs, to the stable set polytope of perfect graphs. I don't think I'll get to that. But there's a nice application where there's a protocol of, I think, n log n square length, and that gives you some quasi-polynomial upper bound on the size of the extension complexity of the stable set polytope. Okay. Good. It can have reals, yes. Yes. So at the end, in communication complexity, in most cases, people study like 0-1 functions and 0-1 matrices.
What I meant is, I guess it's a little asymmetric.
the number of vertices could be different from the number of the rows and columns.
Yes.
So the bit strings X and Y, I guess, could have different lengths in this case, I guess, right?
It's kind of, in some sense, but it's irrelevant what's the bit length of X and Y. Okay. So, so this is the upper bound I just explained. The extension complexity of a polytope, it's upper bounded by 2 to the deterministic communication complexity to figure out what entry you have in the Slack matrix. I said something about a lower bound, and the lower bound that I gave you was the rectangle covering number of the Slack matrix. Okay, so that can also be translated in the language of communication complexity, and the rectangle covering number, it's actually 2 to the non-deterministic communication complexity that two players need to figure out whether there is a positive entry in the Slack matrix or not. Non-deterministic because it's covered, it's not a partition. Okay, good. So staring at this, you see the following. It's like there's an upper bound. There's some kind of protocol that seems to be too strict. There's a lower bound that kind of seems to be like, give too much room to the players. The question could be, is there actually some kind of model, some kind of communication complexity model that captures precisely this size here? And so the answer is yes, there is one, and that's some joint work of Sam, who is in the audience, I hope. If he hasn't skipped the talk, and a couple of other folks. Okay. On the other hand, if he's not in the audience, I don't have to pay the copyright. I have to. Okay. Okay, good. So here's the exact model that corresponds to the logarithm of the extension complexity, or the non-negative rank of the Slack matrix. Okay, here we go. Again, two players, Alice, Bob. Alice gets a row of the Slack matrix. Bob receives the column index of the Slack matrix. Now they run a protocol, but they can use randomness. So they have their own infinite pile of random bits. And okay, now again they exchange 0, 0, 1 bits, and at the end, one of them outputs a number. Imagine one of them writes a number on the whiteboard. And it better be a non-negative number. And what they need to do is, they need to compute the entry in the Slack matrix in expectation. Meaning that over the randomness of the protocol, what they output on average should be precisely the value of the Slack matrix. And that's the right model.
This is correlated randomness? I mean, can it be correlated or?
Okay. The equivalence proof that I'm going to show you, they have internal randomness. Oh god, there are some results about like the difference between like joint randomness and internal randomness, but that workshop was like 2 workshops ago, so I'll refer to that. Okay. Okay. So yeah, I want to show why actually this is kind of the same. And here we go. Okay. So again, there are 2 directions in the proof that I should better show. And okay. So let's say. Okay, let's start with one direction where I have my non-negative factorization of the Slack matrix, and this is a size R non-negative factorization. And now I have to show you how can I get a log R protocol out of that does the right thing. Okay, so Alice just knows the row of the Slack matrix. Bob knows the column of the Slack matrix. They have to compute this entry in expectation, and they have randomness, and they should only use log R bits. And here we go. Alice does the following. she looks at her vector ui, and she picks a random entry, but not uniformly. Sorry, this should be a ui. So she picks the entry, an entry proportional to, well, the value. Okay, so if this is let's say 0, she would never pick it. So this is proportional to the value, and then she sends that index, which is a number between 1 and r. She sends that index to Bob. So she uses only log r bits. Now Bob gets that index. Now Bob stares at his vector, and he outputs the value of his vector. And again, like v at u and v, I messed things up here. Okay, good. If you now look at what are they, okay, Bob outputs values depending on the randomness. So what is the expected value that he outputs? Well, the expected value, well, you just write down the expectation, what it is. It's you're summing over, these are your events, this is the probability of the event, and this is what is being output in that case. But this is precisely the inner product. And the inner product is what they have to output. Okay, so not much happened. Okay? So this is one direction of the equivalence. For the other direction, that works as follows. So imagine this is the protocol tree. Alice and Bob, they exchange C bits, and at the end they output on average the entry in the Slack matrix. So if they do that, then where's my factorization that has size at most 2 to the C? Well, let's do the following. Let's think a little bit about what we actually get. So at the end of the day, what we are getting is the entry in the Slack matrix, and this is the expectation. So we may end up at every of the leaves. Bob or Alice are going to output some value that's going to be non-negative. There's going to be some probability that given this input I and j, the protocol ends up at that leaf. Okay? Good. But if you think about this, if you fix a leaf and you fix some input I and j, and you're wondering what's actually the probability then that we end up at that leaf, then it's actually the probability that in all the rounds that belong to Alice, you're staying on the path going down to the leaf, and in all the rounds that belong to Bob, you're also staying on the path that goes down to the leaf. So these are two probabilities that you'll just have to multiply. So given Alice's input I, you take the probability that Alice stays on the path, and given Bob's input j, you have the probability that Bob stays on the path. Now looking at this, actually what you have is that you're writing an entry in this Slack matrix as the sum of, well, 2 to the c many leaves of something non-negative times something non-negative that depends on Alice's input times something non-negative that depends on Bob's input. And that is precisely your non-negative factorization of size 2 to the c. Okay? Questions? Okay, so the message is the extension complexity of polytopes. It's the same as the non-negative rank of the Slack matrix. And the non-negative rank of a matrix, it is very much connected to communication complexity. And in particular, if you want to show lower bounds, it would be a really good idea to look into communication complexity and see what results are there available. Okay, I have a couple of minutes left, so I think I can talk maybe 5 minutes about the last topic I wanted to mention, and then I'll finish it up in the next lecture. Okay, good. So things were a little bit abstract. Let's get a little bit more concrete. And I would love to show you essentially the first lower bound on a concrete polytope. And that was actually the correlation polytope. OK. And here we go. The correlation polytope, it's mathematically defined in a pretty simple way. You just look at the convex hull of all 0, 1 matrices that have rank 1 or 0. OK? So that's nice to write down. For example, in 2 dimensions, we are looking at the convex hull of these matrices here. They have all rank 1 or 0, and they have only entry 0 or 1. OK. We would love to show that any linear program for this polytope has exponential size. That's what we would like to do. So first of all, I would like to mention that this is a polytope that's NP-hard in the sense that if you could optimize a linear function over that polytope, you could actually solve NP-hard problems. That means that you would expect that there is no small linear program representing it, but you still wouldn't know how to prove that. OK. And I think the easiest way to show NP-hardness would be that, well, if you have any graph on n vertices, and if you maximize, and I think this is called the Laplacian over the polytope, then what you're actually getting is the value of the max cut. And max cut is an NP-hard. It's an NP-hard problem, so that's not going to work. OK. So this is an NP-hard it's an NP-hard polytope in some sense, but we would like to show that there is no linear program of small size. OK. And in fact, that's a result of Sam and Masar Pukuta, who's also here, Tivari, and the Wolf. And to be precise, what they showed is that the extension complexity of this polytope, it's exponentially large. So it's kind of as bad as you might fear it should be. The original proof, it worked slightly differently. I would like to show you a simplified combinatorial proof that was later found by Keibel and Weltke. And that's one that one can even nicely teach in some optimization course. OK. OK. There's a principal problem if you want to show a lower bound of this type for an NP-hard problem. Because what it means to show a lower bound, it means you're staring at the slack matrix, which is defined by the vertices, like these guys, and it's defined by the inequalities. The problem is that, what are the inequalities? So it's an NP-hard polytope, and if you would have a nice explicit description of all the inequalities, that would actually give you a co-NP certificate, which is unlikely to exist. So we do have the problem that we have to show the lower bound of a slack matrix that we don't know. OK, that's a little bit of an issue here. However, what we do know are some valid inequalities. OK. So this is a nice family of valid inequalities. And OK. So here we go. For some vector A, you can do the following. You can take 2 times the diagonal matrix of A minus AA transpose. And this times any point in that correlation polytope is at most 1. That's the claim. OK. So why is that true? Well, OK. Easy trick. If you have to show that some inequality holds for the convex hull of things, then it suffices if you show that linear inequality just for every extreme point. Things are a little bit easier. So you can just say that, OK, this vector here, this is a matrix, but it's an extreme point, so it's of the form a 0, 1 vector times itself. OK. Now, if you plug this in here, and calculate what you're getting, well, I try to give a poor visualization. So what I'm doing here is like, okay, this is my vector A. You put it on the diagonal. You put it 2 in front times that vector B transpose. And okay, sorry. You're moving stuff to the other side and subtracting it from 1. So this is A transpose times BB transpose. And I don't know, if you do some pattern matching here, then here, what you're getting is the intersection size of A and B. What you're getting here is actually the square of the intersection size of A and B. And I'm not sure whether the picture was actually helpful. But anyway, so if you figure this out, then what you're getting is that the slack that you have, if you look at this vertex and the inequality belonging to A, then the slack is this quantity, and there's this nice formula that this is actually the square of something, and the square of something happens to be most of the time non-negative. So this is indeed a valid inequality. Okay, so there's our NP-hard polytope. Now we have a ton of valid inequalities. Means that actually we do know a part of the slack matrix. We don't know all of it. But it will turn out that this part of the slack matrix is going to have already a non-negative rank of 2 to the n, and that in the next lecture will lead to that lower bound. And okay, I think it would be a good time to do to have a coffee break, and I'll see you again in a bit.
Any questions before we break?
Yeah, when you think about the inequalities that form the slack matrix, conditions on them, do they have to be non-redundant? Do they have to be passive defined?
Okay, so the question is the constraints that I use to fill my slack matrix, to define the slack matrix. Okay, I think I said let's take the facets. You can take the facets. You can actually just add any valid inequality that just makes the slack matrix larger. Actually, it's not going to change the non-negative rank at all, because you're only adding conic combinations of existing rows anyway. So you can, okay, the answer is you can add any valid inequality, and it's not changing the rank of your slack matrix.
So just to sort of pick up on David's point, so you're just adding a whole bunch of inequalities. You don't have to show any conditions other than they're feasible.
Yes.
Okay, so let's break.